In this section, we're going to examine the standard DHCP packet structures. Now, these packets can get quite lengthy depending on the options that someone has placed in the packets. The trace file I've opened up is called dhcpboot.pkap, and it shows a normal DHCP boot sequence for someone who is outside of their lease time. The first packet that goes out is a discover packet, and the first thing to notice on DHCP packet structures is that we can have packets going out from a source address of 0.0.0.0. And really, this is the only time we should have traffic going out from an IP address of all zeros. The packets go out to the broadcast address, and when the DHCP server responds, you may find that the DHCP server responds back to the broadcast address, or it responds back to a unicast address, the specific address of the target system. I'm going to highlight packet number 1 here, and we'll open up the IP header because we'll see that UDP is coming up next. DHCP sits on top of UDP. And in the UDP header, the ports that we'll see are ports number 68 and 67. Port 68 is the DHCP client port, and port number 67 is the DHCP server port. Now, DHCP is derived from bootp, and that's why we see all the references to bootp everywhere. I'll close down the UDP header so that we can focus on the DHCP header. We begin with the bootp header portion of it, and then later on you'll be able to see some specific DHCP areas down below. Now, the first field is the message type field. We have a request field or a reply field, so it'll either be 1 for a request or 2 for a reply. The second packet is a reply packet, so I'll click on that and we can see it's a boot reply packet. Then we have the hardware type and address length fields, and this is Ethernet, and the hardware address length for Ethernet will be 6 bytes. Now, the hops area really isn't that important to us because in the world of DHCP communications, if we're going to place a DHCP server on the other side of a router, we're going to have a relay agent on our network, and the relay agent will forward our DHCP requests to the DHCP server. The transaction ID number allows us to relate the requests with the replies by putting in the same transaction ID number. And then seconds since elapsed will tell us how long it's been since this client has started asking for an address. When we get to the section where we're analyzing unusual DHCP traffic, we'll see a DHCP client come up and try to get an address, and it's taking a long time, and we'll see this seconds elapsed time grow. Now we're looking at the bootp flags. Now, the first one is unicast, and that basically indicates that this client can accept unicast responses. The server doesn't have to respond using broadcasts, it can respond using unicast. The client IP address is the area where the client says, this is the IP address I have. This client doesn't have an IP address, and so that area is filled out with all zeros. This section where it says your client IP address would be filled in by a DHCP server. So for example, in packet number 2, the server is offering an address, and we can see that the your client IP address field is now filled out with 10.0.99.2. That's the address that the server is offering the client. The next server address field would be used if the responding server is telling the client of another server that it should go through in the next step in the boot up process. The relay agent address, this would be the address of the relay agent that sits between the client and the DHCP server, the one that's helping that DHCP query get up to the server. The client provides its MAC address. If the server wishes, it can provide a host name. And there's a boot file if required. Now, the magic cookie area is interesting. This was originally put in there so that vendor-specific information could be placed in this cookie. But if a client doesn't have any vendor-specific information to transfer to the DHCP server, it will fill in this field with 63825363, which is actually the equivalent of 99.130.83.99, which is what the specifications require. It's a generic cookie. Now, this is the area that's most interesting in DHCP communications, the options area. So we have an option type 53, the length is 1. Option type 61, the the length is 7. Option type 50, length being 4. Option type 12, length being 9. Option type 55, length being 8. We'll open up these options, and we can see in the first option, it's the DHCP message type option. There's the option number 53. There's the length, and the value is 1. So this is a DHCP message type 1, which is a discover packet. A type 2 is an offer. A type 3 is a request, etc. All of these things can be found in RFC 2131. I'll close up this option and we'll go to the next one, which is the client identifier option. Basically, here's the client identifier information. This is the numerical value, and this is taken from the client's MAC address. The client's MAC address is 00A0CC30C8DB, and here we can see there's the 00A0CC30C8DB with a 01 in front. If that client has more than one hardware address assigned to another card, so if it has more than one card, I should say, connected to the network, that client system may have more than one address, more than one value in this location. We can see the client MAC address is listed in there as well. The next option is the requested IP address. Now, this client would like to get 10.0.99.2. It's what the client would like to have. The next option is the host name of the client. Then the final option in there is the parameter request list. These are the things that the client would like to know from the DHCP server. When we see a server reply, it takes the same format. Now the options are a lot more interesting. And in the response packet, first of all, we saw before, this will be a reply packet. And now the server will place in the client's IP address. This is the offer that's being made to the client. As we scroll down, we can see that this is a message type 2, which is an offer. The server is identifying itself as 10.0.0.1. And it's saying that you have a lease time of a whopping 5 minutes, and that's it. And here's your subnet mask. Upon receipt of that, we see another packet go out, and all the packets have basically the same structure. You'll start out with the boot P area. You go into this area where you'll see all the IP addresses listed, and then the options follow that. Now we're going to take a look at how you can filter on DHCP traffic. First we'll start with capture filter, then I'll go to just a generic display filter, and then we'll build some display filters based on specific fields inside of the DHCP packet. So the first thing we'll do is go to our capture options window, and I'll click on the capture filter button to see if one is already built for me. So I look through here, nope, nothing is built for me yet. So I'll build a filter for DHCP traffic. Now, unfortunately, we can't just type in the filter string of DHCP anywhere when we want to do filtering for DHCP traffic. We would have to put in boot P in the display area, but that isn't recognized in the Wireshark capture filter. I'll show you what happens. If we pop in boot P here, say OK, say that we want to start capturing. A message will come up saying, I'm sorry, but invalid capture filter, boot P. Okay, all right, so we know that's not correct. So what we need to do is we need to make a filter that will look for the DHCP traffic based on the port numbers. So I'll name the filter DHCP, and I'm going to type in port 67 or port 68. Those are the two ports used for DHCP communications. I'll say OK. It's in there, and I'll start capturing. Now I know this network has some DHCP traffic running in the background. So I'll give it just a moment, and all of a sudden we'll see DHCP traffic appear. There we go. We've got a DHCP offer right now. And that's enough to start looking through the packet structures if you were starting to examine DHCP traffic. But I'll let it run for a little bit longer so we have some more DHCP traffic. Now I'm going to go through building DHCP display filters. So I'm going to stop capturing traffic. And I'm going to open up a trace file. And this trace file is called MISC, just miscellaneous. I'll continue without saving. And I'll say I want to open up misc.pkap. Now this trace has a lot of different traffic, not only DHCP traffic, but it's got a lot of web browsing traffic. The easy way to build this filter is to, first of all, not type DHCP, because if you do, you'll see it shows up as all red, but to type bootp and hit enter. And that will pull up the DHCP traffic that's in that trace. So here we can see some DHCP traffic that I have in the trace based on that. In addition, you can pull up DHCP traffic based on individual fields inside of the packet. So for example, if I'm looking at packet number 513, I could choose to just filter on all DHCP boot reply packets by right mouse clicking and preparing a filter based on the selected value. You'll see there's the filter syntax. We can also do a filter based on things such as the DHCP option, that it's a message type. And it says bootp.option.type. Remember that DHCP is derived from bootp. So when we talk about doing any filters, we're actually talking about building bootp filters. There are two different places you can go to get the filter syntax for DHCP communications. One is the Wireshark webpage, and the other is in the expressions area. On the Wireshark webpage, I'll select documentation, scroll down to the complete list of display filters. Now, am I going to hit DHCP or am I going to hit bootp? I'll go to bootp. I'll scroll down. Oops. And there we can see bootp. Now we can see all of the syntax that we can use for display filters for DHCP traffic. It uses bootp for everything. We can also go to the expressions area inside of Wireshark. I'll select expression. And then in the expressions window, I'll type in bootp. And you can see it's listed as bootp/DHCP. Open that area up, and it will show me the different filter syntax that I can use for building my display filters for DHCP communications. Now we're going to look at normal DHCP communications. I'm going to start out by looking at a normal DHCP client getting an address from a server doing the 4-packet process, which is discover, offer, request, and acknowledge. And then I'll show you what it looks like when you're on the inside of a DHCP relay agent and how the client gets the address from the agent, not from the server directly. So the first trace I'm going to open up is just called DHCP boot. And there's the 4-packet process: discover, offer, request, and acknowledge. In this discovery packet, if we collapse this, I'm going to collapse the DHCP area here, the bootp area, and then open it up so that I don't see all the information under each one of these. But the main thing that's important here is that the client is requesting an IP address. And it appears that the client's going to get that IP address if we look at the offer and the acknowledgement. So that means that the client has been on this network before. Now, it's not within its lease time, because if it were within its lease time, it would simply make a request and get an acknowledgement back. It's just 2 packets when you're inside the lease time. So this is the requested IP address, and there's a parameter list as well. In the parameter list, the client is asking for a number of things. It's asking for its subnet mask, the router, the DNS entry, the domain name, and then information about net bias, as well as information about the maximum DHCP message size allowed. When the server responds to that, and again I'm going to bring this down. I'm going to collapse this all, and then I'm going to open it up. The server responds with a boot reply. Now the server fills out the client's IP address. Now here's where we see all the options again. Now first let me take you to the list, the master list of options that's available online at iana.org. From the main iana.org website, I'll choose Protocol Number Assignment Services and the letter D on the index to get down to fields that begin with the letter D and protocols that begin with the letter D. I'll scroll down to get to Dynamic Host Configuration Protocol. And there are the parameters. I'll click on the parameters link, and here we can see the list of DHCP options. So there's the router option, time server, name server, domain server. If we scroll down a little bit more, you'll be able to see additional options. There's 53, which is the message type. Now let's go back over to our communications and see what else is happening. We can see that the type 53 option, the DHCP message type, it's an offer. And then 54 is the server identifier, so the server is saying that its address is 10.0.0.1. The lease time here, as we saw before, this is really a pathetically low lease time, and then the subnet mask has been given to the client. Now, we're going over to the request packet, the third packet down, which comes from the client. Now, the client is still not using that IP address. Because remember, it's not allowed to use that IP address until it does the gratuitous ARP process, just as we saw in the ARP section of this course. You've got to do that gratuitous ARP process before you can start using that address. But in packet number 2, the server went ahead and started using that address anyway. It doesn't really matter because the packet will be forwarded based on the MAC address, and the MAC address will go directly to that client. So even if that IP address is in use by someone else, it will be forwarded based on the MAC address because DHCP communications is local. Either we get an answer from the DHCP server or we get it from a DHCP relay agent. So in packet number 3, the client sends out a broadcast request again. It's interesting that these are broadcasts. It means that we can pop in anywhere on a switched network and listen to all of the DHCP discover packets and the request packets. Now the request packets tell us pretty much what the IP address of that client is going to be. As we scroll down, we'll see the client gives its MAC address. And then in the options area, the client will say that it wants to request that IP address. The client will also, again, give its host name and then a parameter list. And we'll open up that parameter list, see what the client's asking for this time. The same information it asked for before. So now the client is saying, yes, that is the address I would like to have. Now, if 2 DHCP servers answered this client, the client could respond to one of them with a decline, saying, no, I don't want that. No, thank you. Now we'll go down to the last packet in this set. And in this packet, we have the ACK packet. Now, it's a boot reply. And there's the server saying, your IP address is 10.0.99.2. This is your MAC address. We can see it's a DHCP message type of ACK. It's a value 5. And here we see the server identifier, the address lease time of 5 minutes, the subnet mask of 255.0.0.0. There's the router's IP address, the domain name server IP address, the domain name for the client, and that's the end of the options. So that's the process. It's actually pretty simple until we start throwing in a relay agent. Now, a relay agent would sit on the same network as the client, and it will forward the client's DHCP requests on its behalf to the DHCP server. I'm going to open up a trace file right now called DHCP. I'll scroll down. You can see I have a lot of trace files having to deal with DHCP communications. But this is a DHCP communication. It's called DHCP-relay-client-side.pkap. I'll open this packet up, open this trace file up. And the first thing we see is we see a broadcast going out on the cabling system. The client is sending out a broadcast, and I'm going to collapse all to start with. And here we see the address of the client is this one ending in DB. Now we see a reply coming back from 10.1.0.1. In the IP header, we can see the time to live value of 127, which feels like this packet has been routed because it probably started as 128. Most likely, this communication has been routed through a DHCP relay agent. Now, in the client request that went out, let's see what the client was asking for. I'm going to scroll down, open up Bootstrap Protocol, and we can see the client is asking for an address of 10.2.0.1. There's the client's ID, the host name, and then here's the parameter list, what the client wants. Same thing we saw in that last trace. In the acknowledgement packet, now the server at the top is saying, this is your client IP address that I'm offering you, and there's the relay agent address. If you wanted to find all traffic that's DHCP traffic that's come through a relay agent, you could simply right mouse click and prepare a filter based on the selected value. But maybe I don't want any traffic, just traffic going through that relay agent. Maybe I want it going through any relay agent. In this case, I would say that I don't want bootp IP relay traffic that has 0 in it. If it has 0 in that relay field, then it indicates that this traffic is going through a relay. This traffic is not going through a relay agent. When we apply that, however, look at this traffic. We have some other packets that are showing up. We've got our relay agent showing up right here. Relay agent, relay agent. These are all the packets that have come through the relay agent. So I'll clear this filter out so we can watch everything. So here's the ACK that came back. It came through a relay agent because now we have an entry in there. It's an ACK. The server, the DHCP server, is 10.1.0.1, but we know we're getting this information coming from the relay agent. The client is being offered 3 days as the lease time with a subnet mask of 255.255. The router is 10.2.99.99. The DNS server is 10.1.99.99. Now if we go back up, we can see that there's the relay agent at 10.2.99.99, and that's also the router for the client. We'll go to the next packet. This packet is also coming from the DHCP server. It's another ACK packet. And here, there's the relay agent information. Simply an ACK, server identifier, lease time, subnet mask, DNS server, basic information again. Now this time the client is going to say that it's using 10.2.0.1 and it's going to send information up to the server through an inform. Really it's not sending information up as much as it's requesting additional information. We can see it's a DHCP inform type. Scroll down. And this is what it's asking for, subnet mask, and it's a Novell client. So it's asking for Novell options, SLP agent scope, directory services servers, tree name, and context. We see the client sending a packet. We see the server sending a packet down to the client. The client is giving the router information, domain information, the standard set of information, and then it has a note saying, I'm sorry, this information does not exist on this subnet. So the Novell options are not supported on this subnet, even though the client is asking for it. So that's an example of normal DHCP communications. In the next section, we're going to look at DHCP communications where it's really strange. Things don't seem to be working the way that they should be. I'm going to show you a couple of unusual DHCP communications. The first one is where someone takes an address even though they haven't been assigned an address. The DHCP server is not up and running, but they take an address anyway. The trace file is called dhcp jerk takes address no permission. Now, this is the trace. And if we look at this trace at the beginning, we see the client making a DHCP request. We can look inside that request to find out a little bit more about what is being requested and who's making the request. So I'm going to collapse the boot P area, and I'm going to expand it so it's nice and neat. We see it's a request packet. There's the client providing its MAC address, DHCP message type of a request. Client provides its identifier information, which is basically its MAC address. And then the requested IP address is 10.1.0.2. So that means it had that address before, and that's the address it wants again. The parameters list, we'll see what it's asking for. Just basic information. Now the DHCP server does not reply. We could see that 6 seconds goes by from the original request until it asks again. So I'm going to highlight and click on packet number 2, and we could see the seconds elapsed, 1,536 seconds. Now I can tell you that this DHCP client is not going to be that patient. After this point, this client just goes out and does a gratuitous ARP for that IP address, saying, I don't care what you think, I'm going to go ahead and grab this address, 10.1.0.2. So there's the gratuitous ARP, where it says basically, I'm 10.1.0.2, and who else has 10.1.0.2? Since it didn't get an answer back, goes ahead and it starts using that IP address. Now, if you work in the Windows environment, you know that Windows will automatically take a 169.254 number just because of this potential problem that somebody could be on the network with 10.1.0.2, and just because the DHCP server didn't respond doesn't mean you should start going right after a gratuitous ARP. So that's an example of a weird DHCP communication. Now, if we look a little further in this trace, you will see a DHCP inform packet going out from 10.1.0.2 to the broadcast address. And look, all of a sudden we have a DHCP communication coming back on the wire. 10.1.0.1 is suddenly answering. So as we scroll down, it's a boot reply. The server is acknowledging that the client's address is 10.1.0.2 and the client's MAC address, sending back an ACK, and the server said, I'm 10.1.0.1. There's your subnet mask, there's your router information, there's your domain name server information, and here's the response to your request for Novell options because it doesn't support it. So suddenly our DHCP server has come back online to communicate with the client. Too bad the client already took that address and moved on. Now the next trace I'm going to open up is where we have a DHCP server that's just really slow. It's called DHCP-slow, server slow. Now we're looking at the time column, and my time setting is set to show me the time from the end of one packet, from the beginning of the capture. So I'm going to change it to show me the time from the end of one packet to the end of the next packet. So here we see a DHCP discover go out from the client. No answer. The client waited 6 seconds, but it didn't get an answer. And then finally a DHCP offer comes back. Now remember that time elapsed area? Here we can see the time elapsed, 2,304 seconds elapsed from the original request to the time this packet came in. Now we can build a filter based on the time elapsed value. I'll prepare a filter based on the selected value. Boot P seconds. Maybe I want to build a filter to find out if boot P traffic ever was greater than a 1 second delay between a request and a reply that came back. That's a great filter to build, easy to do, and we just used an existing field inside of a packet. So we see all of a sudden the DHCP offer is made to the client, but our client is still in the process of doing discover. So this offer came across, but our client is still doing a discovery process. We can see the amount of time between packet number 2 and packet number 4 is very insignificant, to the point that the client can't even count up 1 more second in the seconds elapsed area. Now we can see, though, that something else has changed, the transaction ID on the right-hand side. Although the offer was made, the client has gone on and started a whole brand new discover process. We've got a brand new transaction ID, and all of the communications that occur after that point have to do with the new transaction, the new discover request. It's all the same client making these requests, but the client just couldn't wait anymore. It went on and started up a new discover with a new transaction ID, and everything worked at this point. We have the discover, the offer, the request, and the acknowledgement, and now the client is able to use the IP address. We can tell what IP address it is if we scroll down. It says your client IP address is 24.6.150.207. And this is the relay agent that we're getting the address from. You can see the variations in the source and the destination addressing system. In some cases, we'll see the packets come from the DHCP server itself. Other times, we'll see that the packets actually are coming originally from the DHCP relay agent who's giving those addresses out. So we scroll down, we can see it giving us the server identifier. That's the DHCP server. The client has been given a lease for 1 hour. There's the subnet mask. There's the router for the client. And the DNS server for the client. There's more than one DNS server being provided, a primary and a secondary DNS server. And look at that. This is on a Comcast network. So those are some strange communications in DHCP. The other thing you might look for is just duplicates. Anytime you see duplicates, especially in offers and acknowledgement, you might have two relay agents providing information to clients on the same network.